All right, well, here's 10.6, and obviously the last section of Chapter 10. And our objective today is to write polar equations of conics. So we'll take our conics, our parabola, ellipse, and hyperbola. We won't be using a circle at all today. And we'll be writing those in forms of polar equations. So remember, polar equations, they have, our points are theta. And when we do these, our polar equations of conics take simple form if one of the foci lies at the pole. So you will always have a foci at the pole if you are going to write a conic as a polar equation. So how we do this is we are going to classify our conics according to the eccentricity of it. And remember that your eccentricity or eccentricity, whatever you want to call it, is C divided by A. And just to go through and review our conics a little bit, we will have F, which is going to be a fixed point, or our focus, and that is going to be, remember, we have to have one at the pole. D is our fixed line, or our directrix, and we really only talked about having a directrix with a parabola, but there's a directrix also when graphing an ellipse and a hyperbola. And then P will be any point on the graph. And we have to be able to identify these. So we have our fixed point, our focus point, which will be at the pole. D is our representative of our directrix, which is a fixed line, and P can be any point on our graph. Well then, when we have our eccentricity, it is the ratio of the distance between the focus and the point. So the focus and the point to the distance between the point and directrix. So running out of room a little bit, but remember, a ratio is a fraction. And our fraction here, it's the ratio, so the distance between the focus and the point, so we want to find that, that distance will be in our numerator. 2, so in the denominator, the distance between our point and our directrix. Well, what that ends up being then, for our eccentricity, is that eccentricity is focus to our point divided by, for our ratio, point to directrix. So if we start with a parabola, our parabola is going to have an eccentricity equivalent to 1. And so that's how we will be able to identify that we have a parabola. And if we graph, we know that we have to have, our focus has to be at the pole. So we have to have our focus right here. And we go around our focus point, so I'm just going to sketch in any parabola there. We know for a parabola specifically that this vertex, the spacing is equivalent from your vertex to your focus, as well as from your vertex to your directrix. So if I draw my directrix, it would have to be down here. Oops, I missed it a little bit. Your directrix will never ever intersect your graph. And so with a parabola, here is my focus. You can pick any point now on your parabola. So I'm just going to pick point P. So I have that distance and that distance. My directrix might be a little low there. We know the definition of parabola, that those two things are always going to be congruent in length. And so because they're always the same, if I look at the distance from my focus to the point divided by the point to the directrix, well, because they're the same, that will always equal 1. For an ellipse, we know that our eccentricity is always less than 1. And when we graph, we've never graphed an ellipse with the directrix, but we definitely have that. Remember, one of our focus points has to be at the pole. And I'm just going to, so here's my focus. I'm going to draw my ellipse to be horizontal. So if I have a horizontal ellipse, in this situation, my ellipse is horizontal, so my directrix is going to be perpendicular to that. So my directrix will have to be vertical, and it would be over here somewhere. It has to, when we want our directrix, it's going to be closest to the focus point at the pole. So here would be my directrix for this one. And then if I take any point on my ellipse, so I'm just going to take a point here, and it doesn't have to be this, it could be way over here if we wanted it to be. But if I look at that ratio of focus to a point divided by the point to the directrix, that will always be less than 1. So this distance will always be less than this distance. And again, when you set up your ellipse, so if our ellipse is horizontal, so it's along on the horizontal, then your directrix is going to be vertical. And it's not going to be way over on this side. We want our directrix to be closest to the focus point at the pole. And even if we picked a point way over here, so here's another point, well, that distance is still obviously shorter than that distance. So you really could pick a point anywhere on the ellipse. And then the last one that we have is our hyperbola, and here eccentricity is going to be greater than 1. So if we graph this, again, we have to have a focus point at the pole. And I'm just going to sketch one. I can just have my hyperbola look like this. So here's one branch. Here's the other branch. With your hyperbola, your directrix will always fall between the two branches. And it won't be right in the middle. So don't draw it right in the middle, because it's not going to fall right in the middle. And also remember that your directrix cannot intersect your graph. So I'm just going to draw it here. That kind of looks like it's in the middle. I might try to make it a little bit closer to one of the branches, just so that you know that this does not go through the middle of your branches. And now when I take a point, so when I look at my focus to a point divided by the distance from the point to the directrix, well, this value, this distance, is always going to be greater than this distance, and that's why it's greater than 1. And here you might want to take a note, or write a note for yourself: directrix not in the middle. And also know that your directrix can never ever intersect your conic. So that's just kind of a general idea. We had parabolas because we graphed the directrix when we first graphed parabolas, but that's how you graph your ellipse and your hyperbola, and with a directrix in there. So if we have to see what the polar equations are of conics, we have two options, because we can either have a vertical directrix or we can have a horizontal directrix. And you have to identify right away which is my directrix going to be, obviously vertical or horizontal. And then to write our polar equation, remember we need r and theta if we're writing in terms of polar. So r is going to equal the eccentricity times d. And d, if you go down below, d is equal to the distance between the focus at the pole and the directrix. And this is sometimes difficult for us to find. Remember, whenever you're calculating a distance does have to be absolute value. So when we say distance, it will be the absolute value, but in your work, we'll have an example here where our distance is actually a negative number. But when we actually say, well, our distance is equivalent to whatever it may be, it does have to be positive. So that's a little bit tricky because in the equation, this distance can be negative. But it's the distance between your focus at the pole and the directrix. So our equation is eccentricity times our distance divided by 1 plus or minus eccentricity times cosine theta. Well, horizontal directrix is the exact same formula, except for instead of cosine, it is sine. So R is equal to eccentricity times your distance divided by 1 plus or minus eccentricity times sine theta. Well, the plus or minus, we have to identify which way it's going to be. And if it's a vertical directrix, so you're using cosine, if it's positive, the directrix is to the right of the pole. And then obviously if it's negative or subtracting, the directrix is left of the pole. And for horizontal, your directrix is either going to be above or below the pole. Well, if you are adding, the directrix is above the pole. And if you are subtracting, directrix is below the pole. So when you write your equations, eccentricity times your distance divided by 1, it's either plus or minus, and pretty easy to determine. And then it's your eccentricity either times cosine of theta or times sine of theta, depending on your directrix, whether it is obviously a vertical directrix. And here's how you can remember vertical. If you remember the definition of cosine, cosine is x over r. So cosine is x. X is a vertical line. So that's why that one works out. And then sine, the definition is y over r. Well, y is a horizontal line. So you know that's kind of the relationship and why one uses cosine and one uses sine. All right, so now we have some examples. We want to determine the type of conic. We have to identify our eccentricity. We have to identify the distance. And then we want to sketch the graph labeling the main points. I'll be specific on your quiz and test what I want, but main points, usually I'm looking for your two foci, and depending on what your conic is, I'll be looking for your vertices, usually vertices. I guess if it's a parabola, you just would have one. So the first thing that we have here, r is equal to 5 divided by 5 plus 3 sine theta. Well, the first thing that you have to do is this value, this thing, has to be a 1. And that's just the equation. It says you have to have a 1 there. So that's always the first thing you want to fix or create. So if I have to divide by 5, we better divide that term by 5 and our numerator by 5. Well, now our denominator is 1 plus 3/5 sine theta. And our numerator is a 1. This allows us, though, to set up, and we know basically the type of conic that we have here, because remember, this position in front of our sine or cosine, that's E, so our eccentricity. So we know that our eccentricity is 3/5, and we know in our numerator it's eccentricity times distance. Just if eccentricity is 3/5, our distance has to be 5/3, so that when we multiply them together, we have 1. Well, if eccentricity is 3/5, we also know that we have an ellipse. So we've determined our type of conic, we've identified eccentricity, we've identified our distance, and now we have to sketch our conic, labeling our main points. All right, so if we sketch our conic with this, we know that we have to always have one focus at the pole. So I usually call my focus, I just put an F by there to represent that that's the focus. Well, if I'm dealing with sine, I know that my directrix is going to be horizontal, and because this operation here is addition, I know that it's going to be horizontal and it's going to be above the focus. So if I look at that from my focus to my directrix, it has to be 5/3. So that would be, yeah, maybe I should put in here, like here would be 1, here would be 2. So 5/3, we can draw that in. And there is our directrix. It's kind of weird to mix polar and rectangular, but that is a horizontal line, so I know that that is equal to, y can be equal to 5/3, and we can write, well, that's our directrix. Now remember, when we sketch an ellipse, if our directrix is going to be horizontal, our ellipse is going to be vertical. They're always going to be perpendicular of each other. Well, what we want to do is find specific points. So if I have to find points that have to be on my ellipse, so points on ellipse, what I'm going to do is, I know that I have to have a vertex point going up and I have to have a vertex point going down. Well, what I can do is plug in a theta value. So if I know that I have to have a point and I want it here, I can plug in pi/2, because that would be my positive y-axis, and then I can solve. So I'll write a note to us that our vertices are, when maybe, yeah, are where, I guess, theta is equal to pi/2 and 3 pi/2. But we do have to look at these and adjust and make sure that they make sense. So if we have pi/2, remember theta, that would be our the second coordinate there. If I plug that into the original equation, or I could plug it into this equation, it really doesn't matter. Then I'd have r is equal to 5 divided by 5 plus 3 sine of pi/2. Well, I know sine pi/2 is equivalent to 1. 1 times 3 is 3, plus 5 is going to give me 8. So then I would have 5/8, which makes a lot of sense. So here, and it's just approximate, it's a little bit greater than a half. Here would be 5/8, and there is a vertex point, but here is a point specifically labeled. I also know that I can test 3 pi/2. Well, for 3 pi/2, I would have 5 divided by 5 plus 3 sine 3 pi/2. Sine of 3 pi/2 is -1. So -1 times 3 is -3, plus 5 is going to give me 2, and now that would give me 5/2. So if I go to 3 pi/2 down here, that would be 5/2. If I try to do even spacing from above, that would be 3. So 5/2 would be right here for my second vertex point. And now I have my vertices. I'm not too concerned about the width of this, but I do want to see where the vertices are. The other thing that we could possibly do is find our other focus point. And what we know is that we have to have even spacing here, just with conics. So if we know that we go 5/8 up to this point, we know that we have to move 5/8 from this bottom point. So you could, here are your two vertices. We could write down that our other focus point, obviously we have one at the pole, so we could say 0, 0. Our other one, I would say it's at 3 pi/2 because you are going down. And then I would take the 5/2. Gotta grab my calculator here. And I'm going to subtract 5/8 from it to bring me up to here. So if I subtract 5/8, that gives me, as a fraction, 15/8. And that goes back to section 1 and the stuff that we know about conics, that we do have even spacing. So that would be the other focus. So you have a focus point here and at the pole, so 0, 0. Looking at another example of this, number 22, r is equal to 4 divided by 1 plus 2 cosine theta. Well, this one's really nice because we already have that position of a 1, and that's the first thing that we have to determine. So that's great. We really don't have to alter this equation. We know that when add or subtract, that doesn't matter. This is your eccentricity, so we know that that's equivalent to 2. Well, if that's 2, here we have eccentricity times distance. We know our distance is 2. And with our eccentricity equal to 2, we know our type of conic. It's obviously it's greater than 1. This is going to be a hyperbola. So with this, we can start to sketch. And we have to have a focus at the pole. So there's our focus. I know that I'm using cosine. So if I have cosine, my directrix is going to be, cosine, remember, deals with your x's. So my directrix will be vertical, and I'm adding, so I'm going to go to the right. So from my focus to my directrix, that's what that distance represents, that's 2. So I can easily graph in my directrix. Here's our directrix. In rectangular sense, it would be obviously where x is equal to 2. Well, again, if we go back to the directions on the last page, I told you to determine the type of conic. Okay, great, we have our hyperbola. We identify our eccentricity, which is 2, our distance, which is 2, and then we have to sketch labeling our main points. So again, we have one focus. We have to find our vertices. And so when we find our vertices, now in this situation, we know that our branches cannot intersect the directrix. So our branches are going to have to open to the right and to the left, like this. And therefore, again, if we look at like our, try to find theta, we really only have where theta is 0. So it's where theta is equal to 0, because they're both probably, well, they're both going this direction. But we can have theta equal to 0 or theta equal to pi. Because pi, we can get a negative value to go this way. So where theta is equal to 0, to find our point, we would say r is equal to 4 divided by 1 plus 2 cosine 0. Cosine 0 is 1, times 2 is 2, plus 1 is 3, and so we'd have 4/3. So 4/3 0, 4/3 will be about here. That makes a lot of sense. We have a directrix, and I'm not too concerned about the width of the branches. I just want the main points and a general sketch, so good enough. And the width could be completely off, but not too picky about that. All right, well then our other one, if theta is equal to pi, because you're always testing, you know, here's 0 or pi, but it's always on that line. So we have r is equal to 4 divided by 1 plus 2 cosine pi. Well, cosine pi is -1 times 2 is -2 plus 1 will give us -1. So we have 4 divided by -1, which is -4. So if I have to go pi, but I want -4, well, that makes sense because that's going to put me over here at -4. And try to make your branches look symmetrical. But that makes a lot of sense in that we know where our branches have to be, and now this point verifies that that works out. So there are our vertices, and then if we talk about our foci and identify those points, we know that we have 1 at the pole, so 0, 0. And the other one, again, remember it has to be even spacing. So if I look at this distance, which is 4/3, we'd have to go 4/3 this way as well. So I would also have one, and you could call it, oh boy, 4 plus 4/3 is going to give me 16/3, I believe. And you could either call that 0, or this same point, you could say -16/3 and pi. I really don't care. I think this first one is easier. So I think that looks pretty good. All right. This last example, and why we have to put this in here is we do have a little, something that's a little bit a change. We're going to end up having a negative that we're going to have to deal with. So when we look at our equation, okay, obviously we have an issue because now we're back to having a number other than 1 here. So right away, we start by dividing everything by 4. Now our equation is going to be negative 3/2 divided by 1 minus 3/4 cosine theta. I'm going to draw a little line here to make separate. Well, in this situation, here's the first time that we've had a negative in the numerator, and that's pretty common, actually. And eccentricity can't be negative, so we're going to put that as, we know our eccentricity, if we look here, has to be 3/4. And then 3/4 times what is going to give us negative 3/2? That would be a negative 2. And really for your distance can't be negative either. So when we actually say our distance, we'll take the absolute value of it. But this will, really the negative should go with the distance because it is going to affect where the directrix is. So there's our numerator. Our denominator, 1 minus the 3/4 cosine theta. To identify everything, our eccentricity is 3/4, so we're back to graphing an ellipse. Eccentricity is 3/4. Our distance now, it has to be a positive 2. So I know it's a negative, but that can't, we have to take the absolute value of it. When we graph though, that negative is very important. So I know that, okay, I have my one focus at the pole, and cosine is your x's, so I'm going to have a vertical line. And this vertical line, right now it looks like it should be to the left of the pole, but this negative, actually, it's like multiplying by a negative, it's going to push it to the right, because you're going to the left, but you're going a negative value, so you end up going to the right 2. So here is where our directrix is going to be. And so, just to repeat, cosine is vertical, a vertical directrix. Negative means it should be to the left of the pole, but a negative distance makes it go to the right of the pole. So then there's your directrix. And now we're graphing an ellipse. So an ellipse is going to be perpendicular to your directrix. Therefore, when we find our vertices, we can have, for theta values, we'd plug in 0 and we'll plug in pi. So if we have 0, put it into our equation, and I just go back to the original equation. So I have negative 6 divided by 4 minus 3 cosine 0. Cosine 0 is 1 times 3 is 3. 4 minus 3 is 1, so I have negative 6. So 0, negative 6. 3, 4, 5, 6. And that would be a negative 6 in there. Now the other one that I'm going to plug in is pi. So r is equal to negative 6 divided by 4 minus 3 cosine pi. Cosine pi is negative 1 times 3 is going to give me negative 3. 4 minus negative 3, I think that's right, I got to calculate again. Cosine of pi is negative 1 times 3 is negative 3. 4 minus a negative 3 will give me 7, so I have negative 6/7. So for pi, I have to go a negative 6/7, which will put me this way, which makes sense. That's how we predict that it's going to be. There's our ellipse. If we find our foci, we know that one of them is at the pole, 0, 0. And the other one, remember this is 6/7, so this distance would also have to be 6/7. And multiple ways to write our point. If we are at negative 6 and we add 6/7 to it, write it as a fraction, you should have negative 36/7. And if I have it negative 36/7, then my theta value has to be 0. Or you could write this point as a positive 36/7, and then theta would be pi. All right. So those are the first type of examples. I don't know if you have to go back and review any of these things. Pretty common questions, a lot of them deal with this. And next, we will be dealing with the next type of question.